Click on that. Let it flip out. Go ahead and flip out. I know you're going to. Oh, now it's going to give me all that good stuff. All right. All right, where's the pointer thingy? All right, well, now I get to practice my editing and see if I can cut off the beginning of this thing. Let's see. All right, well, I'm not sure what's going to work and what's not going to work, but here we go again. Well, it's not going to work. All right. I don't know why it's doing that, but that's okay. All right, so this is voltage drop, and we're going to talk about the formulas for this single-phase voltage drop. The formula is 2 kil over circular mil gives you VD. I can't hear you. 2 kil over circular mil gives you VD. One more time. 2 kil over circular mil gives you VD. That was pathetic. One more time. 2 kil over circular mil gives you VD. Okay, now what that means is for single-phase circuits, 2 KIL divided by the circular mil gives me VD, the voltage drop. Still not working. All right. Where K is the constant 10.8, and we are going to use 10.8, not 10.4 or 14 or 21. Mike Holt uses some strange number like 14 or 21, but he didn't do the work backwards from the code book, where the 10.8 is based on a temperature of 30 degrees centigrade, which is the deration point of wire on our cables. So 10.4 is actually rated, is a temperature. If you work backwards, you find that that is the, assuming a temperature of 20 degrees centigrade, which is an ambient temperature that just doesn't happen much. Where 2 times K, why 2 times? Because the current in a single phase circuit goes out and comes back on the neutral, right? So it's double the distance in a way. I is the current, and that's the most effective thing we've talked about when we transform voltage to send it across long distances. We kick the voltage up to lower the current, because the current is what the voltage drop is based on. The length in feet, and then divided by the circular mil wire area. Something you generally cannot change once you've installed it is the size of the wire. But before you do that, you can make that selection, and that gives you the voltage drop. Now, that's very nice and good if you want to find the amount of voltage that has been dropped. But we don't. Let me see if I can do this. Does it really?
Yeah, take a look. There it is. Circle on it. Follow where your hands are.
Huh. Oh, well. Not working the way it ought to, but that's okay. Now, the formula, VD formula for finding the minimum cross-sectional area is what we want, because when we're installing wire, we don't know what the voltage drop is going to be. We want to make sure that it doesn't exceed a certain amount. Now, voltage drop is not a code requirement unless the city, county, or the authority having jurisdiction has decided to include the fine print notes, which generally are advice. But some areas choose to adopt the fine print notes, such as City of Los Angeles, meaning that you should follow that advice, because if you don't, it's a code violation. So, to set something up so that you don't have excessive voltage drop, you can use this formula, 2 kilo over the voltage drop you want to allow, or minimize the voltage drop to, will give you the circular mill area, minimum area. We'll come back and do some examples with that, hopefully. Single-phase circuit formula, voltage drop for 3-phase circuits. When we're doing a 3-phase, it should just say voltage drop formula for 3-phase circuits. Instead of using 2, we're using the square root of 3, which is 1.732, which we use in a lot of things. So we're going to use square root of 3 times kil divided by the circuit mill, and that will give us our voltage drop. But again, that's not what we want to do when we're designing something or we're installing something. We want to ensure that we're not putting in a circuit that's going to have excessive voltage drop. So what we will do is we will change this formula to the square root of 3 times KIL divided by the voltage drop that we will allow. Now, what voltage drop should we allow? Well, from a main service, we can allow up to 5%. For coming from any sub-panel, you want to assume that you've already lost 2 and you don't want to allow more than 5 total. So you want to allow no more than 3% voltage drop from any sub-panel. So when you have a given problem, you're going to assume 5% maximum voltage drop from a main service and 3% from a sub-panel. Everybody clear on that? Okay. All right. So to find how long a particular circuit with a specific load might be, what is this saying? This is saying that if you want to find out for a specific load, let's say you're wiring a house, and you want to know how far you can go with, say, a number 14 wire without having excessive voltage drop. Can't you flip this formula around and say, okay, the length, if we get this formula, 2 kilo over circuit mill, it gives you voltage drop, we can rearrange this to L is equal to voltage drop times the circular mill area divided by 2KI. Okay? And what will that tell you? That will tell you the point at which a single-phase circuit, whoops, sorry about that. Let me run down to the last one. Because now, if you do that formula for, say, how much can you load a 20 amp circuit, for instance? Let's say you have a 20 amp circuit. You've got a 20 amp circuit breaker, and you've got a number 12 wire. That's all set up for 20 amp circuit, right? How much of that can you use? You don't want to load wires more than 125%, so you can, flipping that around, that means that 80% of that is what you can use if it's going to be a continuous use purpose, right? Okay. So 80% of 20 amps is 16 amps, right? So if we plug in 16 amps, and we have, let me see if I can go back to the last formula. And now let's see if I can write on this thing, and I hope I can. Let's plug in that we have, we want to allow no more than 3%. Oh my God, look at that. And what is the cross-sectional area of a number 12 wire? (6,530 circular mill). Yes, that's correct. And now we're going to multiply that times 2 times 10.8. Times, what is I? Our current, right? 16 amps. And that's going to give us how long can we take a number 12 wire out before it's going to have excessive voltage drop. Let's get our TI-30X2S out and plug in. Well, wait a minute. We want to get rid of 3% because that's not what we have. Oops, sorry, wrong one. What's 3% of 120 volts? 3.6. So it's 3.6, which is the voltage we want to have no more than this amount of voltage drop, times 6530 divided by parentheses 2 times 10.8 times 16, close parentheses, enter, gives us what? Hello? How much? So if you have a number 12 run in a house, you should not make that run any farther than 68 feet. What happens if you go over, say, 70 feet? You're going to have excessive voltage drop. So knowing that, you're going to have to go to a larger size wire to limit the voltage drop. All right, there's a good example. Oh, going to leave that on there forever and ever, huh? All right. Now, let's say that we have a three-phase circuit. What was our, let's go back to our three-phase formula. We'll just go up a few slides. Okay, so we have our three-phase formula. And let's do a calculation, except we don't want the voltage drop, we want the next formula. Because we want to find the size of wire. We want to find the size of wire that we can use to do a certain thing. So let's say that we're going out with a three-phase circuit and we're going out to a 5-horsepower motor. Okay. Actually, let me hit pause for a second. Okay, so let's look at this formula here. And we're going to use this formula. And we're going to say square root of 3 is 1.7321 about times 10.8 times the current, which is 15.2, times the length, which we're going to say is 125 feet. And all that divided by the voltage drop we're going to allow. And since it's a 230 volt circuit, we want to allow no more than 6.9 volts. So now we can see that if we multiply the 1.7321 times 10.8 times 15.2 times, you know what, I think I chose the wrong voltage. I mean the wrong distance. Times 150 feet. So if we have all this divided by 6.9 volts, we wind up with 61.81. Even at 150 feet, since it's three-phase, we don't have an excessive voltage drop because 6530 is number 12 wire. All right? Which is larger than 6181. So now we're going to flip this around, and we're going to see our actual voltage drop if we plug in our formula to find our voltage drop. We'll divide by circular mill instead of voltage drop and find our actual voltage drop. Times 10.8 times 15.2 times 150 feet. And now this time we're going to divide by 6530, which is the actual size wire we're going to use. And that'll tell us our actual voltage drop. So now We're going to pull out our handy-dandy TI-30X2S calculator, and we're going to put in square root of 3 times 10.8 times 15.2 times 150, and hit equal. That'll give us a really big number. We're going to divide by 6530, and it tells us that our actual voltage drop is only 6.53 volts, which is well below our 6.9 volts. So that would be an appropriate wire to use. We can use the number 12. And I hope that's a good example. I think we're going to stop there. Well, we're going to pause. I guess we've got to be recording to change slides. And it's not going to change slides. Okay, in that case, we're going to stop here. Since I can't change slides for some reason. I don't know why not, but that's all right.